Hello and welcome to Measuring Dose Response in Biomedical Research. I'm Dr. Mark Williamson for Transcend. This is a short video for the Professional Development Course short video series. Let's get into it. So, first big piece of dose response, the what. What even is dose response? That's something I wanted to learn more about. So, this is sort of an introductory, first toe dipped in the water type of exploration. It's helped me understand it better and some of the statistical methods behind it, and hopefully it helps you. So what is it? So simply put, it's the magnitude of the exposure to something like a stimulus or a stressor, so positive or negative. So that's usually like a drug, and then its biological response. So a dose of a drug or another exposure, and then the response, a biological response. That's where we get dose response. It's very common in fields, subsets of biomedical research like pharmacology, toxicology, even things like epidemiology in some circumstances. And an important quote from Pericles is a very common quote in toxicology is the dose makes a poison. So if you're a higher dose of something, you're going to have a higher response typically. Or vice versa if you're having something like a drug for like an inhibitory effect. And so some of the features of a dose response that sort of makes it a little bit different than other sort of statistical modeling is that typically we look at the features of potency, maximal efficacy, and slope. So potency is the location of a curve along a dose axis. So the image I have is of a classic dose curve on the or dose response curve. On the y-axis is wherever the response is. So in this case, this is tissue response. And on the x-axis, we have the dose, and it's almost always shown in log. And so for every tick mark, it's up, you get 10 times the dose. So sort of 1 here, 10, 100, 1,000, etc. And so potency is, the location of the curve along the dose axis. So more potent things are going to have, a curve that goes closer to the left in this sort of circumstance. Less potent are going to be further along here. Whereas maximal efficacy is also known as the ceiling effect, is the greatest response. So sort of where that actually tapers off. So we can see for our curves here, it tapers off at about max efficacy, but you can imagine other curves here. Let's do a green one where that's shallower or even shallower. We see that those are lower. So that's maximal efficacy. And then finally one is slope. So that's the change in response per unit dosage. And so we can see here that for like the red ones, those will have the same slope. But say if we do like a blue one here, we could imagine even steeper slopes or even much more shallow slopes. And the classic dose response curve is going to have this what's called sigmoidal or S-shaped, particularly when plotted with the log dose. And the reason this classic sort of S shape, this sigmoidal shape, appears so often in dose response is why there's usually particular methods to model that rather than, say, simple linear regression. Right, moving on to more of the example of the what. Here's another example of some dose curves here. We have hypothetical drugs, X, Y, and Z, the dose, then whatever the response is. We can see here that drugs X and Z, they have the same maximal efficacy up high here, but we can see here because the X, that curve, even though the slope's the same, it occurs earlier along the dose axis, that has higher potency, so it acts faster and sort of achieves its max efficacy faster. So say this was a drug to painkiller, maybe this would take 2 pills while Z would take 3 or 4. They still like have the total of highest efficacy, so maybe total remission of, say, a headache, but one just takes more of the dose to do so. Whereas Y, we can see here that actually has a lower maximal efficacy than X or Z, and so maybe it doesn't have complete remission of, say, pain. However, if we compare Y and Z, we can see here that it has higher potency, so it starts working faster, but it doesn't work as highly efficient. It doesn't have as high of efficacy as, say, Z. And that's very common to compare different dose response curves to different treatments and to look at which one works the best. And while that sigmoidal shape is sort of the most common or sort of the classic shape, of course, you can have all sorts of dose response curves. The simplest one, of course, would be something like a linear response. So for every unit increase in dose, you get a unit increase in response. In a lot of biological systems that doesn't really work that way. So that's why the sigmoidal shape is more common, especially with the log dose scale. But you could also have other things like exponential, logarithmic, or even some more exotic shapes, like for example, like say maybe a sort of limit. There's some sort of dose limit. So like at certain doses, nothing really changes, but then at a certain limit here, it then shifts behavior. And so you can have much more complicated responses that maybe you need more complicated models to fit. But that's really what dose response is. How a response changes with increasing levels of dose. All right. Next big question on dose response, like how do you actually do it? Like what sort of methods would you do to create dose response curves, sort of fit dose response data? So really it depends on the curve. Broadly speaking, I can kind of think of three big conceptual categories. So on one side of things, we would have the linear side of things. Like if it really is linear, while most dose response biological systems don't show that, maybe some simple ones do. You could just do standard regression model, response as a function of dose. And then on the other side, the more complicated thing to deal with is categorical. Say you don't have continuous dose, you have like low, medium, and high, and then you look at response. You sometimes have to do more sophisticated methods to look at specific dose response. You might need to do things like spline regression, etc. There's not a lot of good resources, very technical, so that's definitely outside of my wheelhouse, and it's outside of an introduction, but there are ways of dealing with it. You should know that. But so the more typical, that classic sort of dose response where you might be fitting a sinusoidal curve, you're going to use that. It's going to be nonlinear. It's going to be something like a gold standard I've seen is the 4-parameter logistic model or the 4PL. But there are other models, other distributions you can use to fit, and we'll see some of those examples in one of the resources I have here. So with that, moving forward, let's dive more into this sort of nonlinear, the sigmoidal curve fitting. So with that, we'll go into our examples. The first examples I have here is dose response modeling in pharmacology in R, a guide. So again, a lot of the software you can use, it depends on what you like to use. R is a good open source software, so that's why these examples are in R. There's some classic dose response, I think like DRC is an R package that's used common, and there's a little more user-friendly one that I'll have in the further references. But with this guide here, they use the 4PL model, the 4-parameter logistic model. So that's going to be the Y variable, your response, as a function of X, your dose. And you're going to have these 4 parameters. You're going to have C, D, E, and B. So C is the lower asymptote. So you think of like where that bottoms out. So the bottom of the curve, whether that's 0 or some sort of minimal value. D is the upper asymptote. So that's going to be your maximum efficacy, so where it ceilings out. Your E is going to be sort of the midpoint, essentially. The EC is like the 50% efficacy, or the IC is like, I think, 50% inhibitory. It really depends on like whether you're doing things like with a drug or like a toxin. Kind of depends on what the dose and what the response mean. But essentially it's a 50% point. That's very useful for a lot of these dose response sort of analyses. And so the steps that this example goes through is arranging your data, make sure you have your response, dose, and if you're looking at different groups, say like different drugs, you need your grouping variable. You're going to choose your curve function. They use the 4PL. Then you fit your model. There's a function, DRM. Of course, I'll have a link to the references. You can go in detail. This is just a broad overview. You look at a summary, extract confidence intervals, and then you can compare across groups. And in fact, that's what they do with this graph here. So again, response, log dose. You can see there's 2 compounds. We can see the efficacy EC50, the 50% efficacy. There's one here for compound A, compound B, and we can see that compound A is more potent. It reaches that EC50 more rapidly. So if this was something like trying to reduction of sort of pain, like a painkiller, you'd want this one has a better potency. It takes effect faster. And it looks like the other setups here, the maximum efficacy is the same. They both go down to 0, and it looks like the slope of the curves are the same. The only real difference between these compounds is the potency. And this was a blog post on Metric or from MetricGate. And again, I'll have the link to this post is in the description and at the end here as well. All right, another example is from this larger work called the TAME Toolkit, and the subsection is dose response modeling. So this takes a little bit of a different tact, where the first one looked at using sort of like a gold standard model, tuning it, and then comparing across groups. This is looking actually at multiple models to see which one fits one set of data the best. And that's another common dose response sort of methodology. And so this training looked at three different models: the 2-parameter log logistic model, so a simpler model, the Weibull model using a Weibull distribution, and then asymptotic regression model. Steps were to plot data, test various curve fits, so the 3 different models here, identify the best fitting model curve, and then derive values from the best model to move forward to whatever additional analysis you'd want to do. And so this is the graph that kind of shows up here, and we see it's looking at the dose as some sort of chemical Z in micrograms per liter. And this is log. We can see it's log fit because each tick mark is 10 times more. And then there's the response is going to be incidence of intestinal tumor. And we see as the dose of this chemical Z, so it looks like it's a carcinogen, as the dose increases, the incidence increases. And they fit these. We can see the lines fit the various models, and they actually have AIC scores. So the lower, the better fit. It looks like the Weibull, the red one, 22.9, has the best fit. And we can see here that, yeah, it kind of goes up and actually recreates somewhat of a sigmoidal model here for the data fit. Fit the model, the data better than the other 2 models. And that's training was from Dr. Roel and Rager for a fall 2021 course. All right, so with that was a fairly basic overview, sort of getting your feet wet, getting my feet wet. Hopefully it's helpful. Here are the references. The first 2 are for more general purpose. What are dose response relationships? 3 and 4 are R packages. So there's the DRC is the more used one, but then the DRDA is nice because it has a vignette. So I think it's a little more user-friendly. You can figure out that yourself. Then the 2 examples from MetricGate, the dose response in pharmacology in R, and then the dose response modeling from the wider training. With that, thanks for joining me. I'm Dr. Mark Williamson, and I will see you next time.